Hello, this is Dr. Strickland. In this video, we will investigate types of errors and their impact on measurements. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. Now, before we go into errors, we've got one more little bit to do with significant figures and how they're handled with different calculations. And this has to do with logarithms and anti-logarithms. So a logarithm actually has two parts, a characteristic and a mantissa. And this is a logarithmic value right here. The characteristic is the number to the left of the decimal. The mantissa is the digits to the right of the decimal. All of the significant figures of a logarithmic value are in the mantissa, and the number of significant figures in the mantissa is controlled by the number of significant figures in the anti-logarithm. So I want to show you that so you can see how this works. So this value right here, a number that you want to take the logarithm of, this is an anti-logarithm. And you can see that there are three significant figures in this anti-logarithm. So if you pop it into your calculator, which I hope you will do, then you get 6.407 something, something, something. Now we can only keep 3 digits past the decimal because there are 3 significant figures in the anti-logarithm. Okay, so this is the mantissa. And this right here is the characteristic. So the number of significant figures in the mantissa is equal to the number of significant figures in the entire anti-logarithm. The value of the characteristic is actually related to the exponent. Sometimes they're exactly the same, and sometimes they're 1 digit off, and that's kind of beyond our pay grade at the moment. All right, so if you go the other way, if you want to do the anti-log of this number, this is the logarithmic value. This is the characteristic. And this right here is the mantissa. So since there are 2 digits in the mantissa, that tells me that I can keep 2 digits, 2 significant figures, in my calculated value here. So since it's an LOG log, it's to the base 10. And this comes up with a bunch more digits than that, but I can only keep 2 times 10 to the minus 4. Okay, and so you can see here, the exponent is not identical to the characteristic in this case, but it's 1 off. And there's, like I say, there's a mathematical reason for that that's beyond us at the moment. Okay, but that's how you handle them. Now, on to the errors. There are 2 big kinds of errors. There are systematic errors, which are sometimes called determinant errors, and random errors, which are called indeterminate errors. Systematic errors tend to be big enough that you can identify them and correct them. Random errors tend to be so small that you generally cannot individually detect and correct them, but the whole basket full of them has an impact on your measurement that we need to deal with. Okay, so systematic errors tell you something about accuracy, which deals with the deviation of a measurement from a reference value. So things like instrument errors, like your instrument needs to be calibrated, is a big example of systematic errors. Anything that causes bias, that is, it makes all of your measurements either all too high or all too low. Reading the meniscus not straight on, either from above the meniscus or from below the meniscus, can cause a bias, which is an example of a systematic error. But basically, they cause a loss of accuracy. That is a higher percent error. And so we see things like absolute error and relative error. Actually, percent relative error is what we call percent error. And you've probably dealt with that before. Now over here on the other side, random errors have to do with precision. How reproducible is this measurement? So things like random electrical noise in an instrument, or personal errors like not being careful in things like interpolation or other very fine skills. So the impact is a loss of precision, which would give you a larger standard deviation. If you haven't done standard deviations before, we'll talk about that here in a bit. All right, but the big difference is that, with systematic errors, it makes all your measurements either too high or too low. But with random errors, you have an equal chance of the measurements being too high or too low. So we'll talk about things like standard deviation and relative standard deviation. So we're going to talk just a little bit about systematic errors and then absolute and relative uncertainty. Okay, so a systematic error is a consistent error that can be detected and corrected using things like standard reference materials, blank samples, or analyzing one sample using multiple methods and then comparing the results. Like suppose that you had a pH meter that consistently reads 7.00 when the pH confirmed by other means is actually 6.92. Now, the absolute error is the actual amount of difference between the experimental result and a reference. So in this case, it would be 7.00 minus 6.92, which would be plus 0.08. And the plus is important because it tells you that the measurements are too high. So you would say that this meter consistently reads too high. In fact, 0.08 units too high. All right, so if you wanted the percent relative error, you take the experimental minus the reference divided by the reference, and you've done this with percent error before. So in this case, it's our absolute error divided by what we know that it is, because accuracy is with reference to the known value. And then times 100, that'll give us plus 1.16%. Okay? All right. Now, let's come down here and talk just a little bit about absolute and relative uncertainty. Okay, with random errors. The uncertainty in a set of replicate measurements is expressed as the standard deviation, which reflects the collective impact of random errors, which are usually too tiny to detect and correct individually. This assumes that all the systematic errors have been detected and corrected, and that the scientist is working carefully and responsibly. So random errors do not include talking about like human error. No, human error is generally under systematic errors, and you can learn how to do things well. So we're assuming that part has been done and that all the instruments have been calibrated. And we're just dealing with the little things that we cannot control. Okay, so suppose that the estimated uncertainty of a calibrated burette is plus or minus 0.02 milliliters, and that you measured 20 milliliters of whatever liquid you were working with. Okay, this plus or minus is your key that we're talking about random error impact and not systematic error impact. Okay, so absolute uncertainty is the actual amount, and sometimes you don't do any subtraction at all. Sometimes it's just right here in the problem, like this. And then the percent relative uncertainty is the ratio of the actual amount of uncertainty to the measured quantity. So that would be plus or minus 0.02 divided by the 20 milliliters times 100 is plus or minus 0.1%. All right, so with absolute and relative uncertainty, you're going to report them with one significant figure, but when we do calculations with them, we will keep a guard digit, and the guard digit is just whatever digit was next when you ran it through a calculator. And if it's a 0, that's fine. It's just whatever was next. And the idea is to prevent rounding too early. But when you report them, when you have a final answer that you need to report, you just do it with one significant figure. All right, so that is the basic story with types of errors and their impact. If you have any questions, please send them to me.